Dear students, as you know, we have studied chapter number 12, Chemical Equilibrium. In the last lecture, we have already studied the Le Chatelier principle, and the topic which is continue is influencing factor of Le Chatelier principle, in which we have already completed change of concentration. In today's lecture, we are going to study effect of pressure. For study the effect of pressure, we have to just remember the ideal gas equation. All of you know what is the ideal gas equation. Ideal gas equation is PV is equal to nRT. Now rearranging the equation and find out the formula for P from this formula. So we will get P is equal to RT into N upon V, where R is the universal constant and we are taking here the pressure at constant temperature. Means we are solving P, means we are solving pressure at constant temperature. So what is the formula says actually? At constant temperature, P is directly proportional to N upon V, because temperature is constant and R is the universal gas constant. So the formula will become P is directly proportional to N upon V, and N upon V, N means number of moles, V means volume. So N upon V is nothing but a C, means concentration, and the unit of concentration of gas is mole per decimeter cube. Now it is about the ideal gas equation, formula of pressure at constant temperature, and formula of concentration. Further, just taking an example of dinitrogen tetroxide N2O4, which gives dinitrogen oxide, means NO2. Student, remember, dinitrogen tetroxide means N2O4 and dinitrogen oxide means NO2. So we are taking an equilibrium mixture of N2O4, and remember N2O4 is a colorless gas, which give, and nitrogen dioxide, and nitrogen dioxide is a brown gas. And this all over the setup we are taking in a silk flask at a particular temperature. I hope you understand. We are taking an equilibrium mixture of N2O4 and NO2 in a silk flask at a particular temperature. Now we are changing the pressure of the gaseous equilibrium. So what we have observed, as we know that N2O4 is a colorless gas and NO2 is a brown gas, and we are taking an equilibrium mixture and at a particular temperature, but pressure is changed. So what we have observed actually, we have observed whenever we decrease the pressure, the color become dark and dark, and equilibrium shift to the right side. Whenever equilibrium shift to the right side, it means that forward reaction is favored and more molecule is formed. Another condition, whenever pressure is increases, color become light and lightest, or almost it will be colorless, and equilibrium shift to the left side. It means that reverse reaction is occur and very fewer or small amount of molecule is formed. So it is nothing but a effect of pressure. When we decrease the pressure, color become dark and reaction move toward the right side and more molecule will be formed. And opposite in increase in pressure, color become lightest and almost colorless, equilibrium shift to the left and fewer molecule is formed. It means that whenever forward reaction occur, there is an increase in number of molecule, and similarly whenever reverse reaction takes place, there is a decrease in number of molecule. We are taking one more example, hydrogen gas and iodine gas, which form hydrogen iodide. As we have seen that there is the same number of molecule on both the side, means one hydrogen, one iodine, two number of molecule, 2 Hi, means both the side number of molecules are same. So there is no effect on equilibrium by the change of pressure. Means change of pressure has no effect on the equilibrium because there is a same number of molecule of the gas on both the side. So it is a effect of pressure on Le Chatelier principle. Now the next is effect of temperature. As you have seen in your screen, there is an equilibrium reaction, phosphorus pentoxide gas, which is break down into phosphorus trichloride and chlorine gas. In this reaction, always remember, whenever forward reaction is occur, it is an exothermic reaction. It means that heat is evolved. Whenever reverse reaction is occur, it is an endothermic reaction. It means heat is consumed in the reaction. Therefore, the equilibrium must shift in the reverse direction because of added of heat. And what does it means? Heat energy is converted into chemical energy. Student, in the reverse reaction, heat is consumed. It means that equilibrium must shift in the reverse. Why? Because heat is absorbed or heat is added in the reverse reaction. That's why equilibrium shift in the reverse reaction. What does it mean? Heat energy converted to chemical energy. Now, let us consider the effect of change of temperature on equilibrium constant. As you know, what is equilibrium constant? Kc and Kp. So here we are taking Kc and we are taking equilibrium reaction. Carbon monoxide react with hydrogen, it form methanol and heat is evolved. Means delta H is negative. Whenever we apply the formula of Kc on this reaction, so what is the formula of Kc actually? Concentration of product upon concentration of reactant. Always remember student, forward reaction is exothermic. According to Le Chatelier principle, with increase in temperature, whenever increase in temperature, the position of equilibrium is shifted to the left side. Whenever temperature is increases, so position of equilibrium is shifted to the left side. That's why concentration of methanol is decreases and concentration of carbon monoxide and hydrogen is increases. Why? Because equilibrium position is shifted to the left side. If equilibrium is shifted to the left side, so concentration of reactant increases and concentration of product decreases. If concentration of reactant increases and product decreases, so Kc is inversely proportional to concentration of product. That's why value of Kc is also decreases with increase in temperature. Student, whenever there is an increase in temperature, equilibrium shift to the left hand side. If equilibrium shifted to left hand side, it means that concentration of reactant increases and concentration of product decreases. And Kc is inversely proportional to concentration of reactant and directly proportional to concentration of product. If concentration of reactant increases, so Kc is decreases. So what is the conclusion actually? With increase of temperature, the value of Kc is decreases. Now, the next effect is effect of catalyst. We are consider here the esterification reaction. Student, you know that what is catalyst actually? Catalyst increases the rate of reaction. Now consider esterification reaction. Acetic acid react with ethanol with give ethyl ethanoate and water. Acetic acid is also known as ethanoic acid. In this reaction, this reaction is carried out without catalyst. If this reaction is carried out without catalyst, so it takes many days to reach equilibrium. And instead of this, if we are adding here catalyst, here the used catalyst is hydrogen ion, means H plus ion. So this reaction completed within a means time is reduces to a few hours. Student, when this reaction is carried out without catalyst, it takes many days. If catalyst is used in this reaction, so time is lower. What does it mean? Catalyst does not affect equilibrium constant and equilibrium composition of a reaction mixture. And also catalyst does not appear in the balanced chemical equation also. Means there is no effect of catalyst. Let us summarize. Effect of concentration. If with the concentration, if position of equilibrium changes but there is no change in the Kc, equilibrium constant. If the pressure changes, even reaction involved in the change in number of gas molecule also, so there is no change in equilibrium constant. But the effect of temperature, if temperature changes, there is change in equilibrium constant. Catalyst no change, equilibrium constant no change, because catalyst has no effect on equilibrium constant. So it is summarized for the equilibrium constant. The next process which we are going to study is Haber process. Haber process is nothing but an industrial preparation of ammonia. The reaction is nitrogen gas react with hydrogen gas form ammonia, and the composition of this is 1:3. Means if 1 mole of nitrogen is used, 3 mole of hydrogen is used, 1:3. Just see that nitrogen is taken from air, hydrogen from natural gas. The volume is 1:3, nitrogen and hydrogen. Condition is temperature is 450 degree Kelvin. Pressure is 200 atmosphere. Catalyst is iron. Ammonia gas is formed when gas is cool and ammonia again turn into liquid, or liquid ammonia is formed. So it is the Haber process. When we are taking the nitrogen and hydrogen gas in 1:3 volume, the temperature is 450 degree Kelvin, pressure is 200 atmosphere, catalyst is iron. So nitrogen gas is formed which is cool and ammonia turn into a liquid, means liquid ammonia is formed. It is the Haber process. Now the Haber process, in the Haber process temperature is in the Haber process the reaction is proceed with the decrease in number of mole. As you have seen, by this reaction number of mole of reactant is 4 and number of mole of product is 2. Means when we are calculating delta n, so delta n is equal to 4 minus 2, it means that it is minus 2. So in this reaction there is a decrease in number of mole, and you know that forward reaction is always exothermic. Forward reaction is always exothermic. Now let us consider the effect of temperature on the formation of ammonia. So The formation of ammonia, as we know that it is an exothermic reaction. That's why whenever we decrease the temperature, equilibrium shifted to the right side. Means at low temperature rate of reaction is small and larger time will be required to attain a equilibrium. But at high temperature reaction occur very speedily or rapidly with appreciable decomposition of ammonia. Hence, optimum temperature is maintained for the formation of ammonia, and that temperature is 773 Kelvin. So, always remember, in the formation of ammonia, when there is decrease in temperature, equilibrium shift to the right side. Means at low temperature rate of reaction is small and longer time will be required to attain the equilibrium. But at high temperature reaction occur very rapidly with appreciable decomposition of ammonia. That's why at optimum temperature required for the formation of ammonia, and that temperature is 773 Kelvin. The next effect on the formation of ammonia is effect of pressure. Always remember, if we are applying the high pressure, so forward reaction is favored, but the number of moles decreases, as we have already seen in the reaction. In the formation of ammonia or in the forward reaction, there is decrease in number of mole. So whenever high pressure is there, forward reaction is occur and decrease in number of mole. At high pressure, catalyst is not sufficient. Therefore, pressure also optimum pressure is maintained, and this pressure is about 250 atmosphere. So it is all about the equilibrium constant. In the next lecture, we are going to study some numerical problem from this chapter. Thank you so much.